0 case, your n will be 3 by 2. Fine? Is these things? No? Then I am erasing this part. So this exponent n for various kinetic condition we discussed can be written as n equal to p plus q, where for nucleation gives the value of p. P will be 0 if all the nucleation events occurs at the beginning, so nu t is very large. That means I t greater than 0 equal to 0. That means site exhaustion P equal to 1 if nucleation rate is constant, if nucleation events continues at a constant rate, if I equal to constant, and growth mode gives the value of q, which will be equal to 3 if it is linear growth rate, growth with a constant rate, growth with a constant rate, and q will be equal to 3 by 2 if it is parabolic growth, that is diffusion control. So you can see those whatever we discussed, that n equal to 3 if it is 0 plus 3, that is site exhaustion and linear growth rate. If it is parabolic growth rate, then it will be 3 by 2 for site exhaustion, but for constant case 1 plus 3 by 2, that is 5 by 2. Okay, so you can determine n experimentally like that from the slope of ln 1 over 1 minus fv, but it cannot directly give you the actual, because n depends on both nucleation and growth. You cannot just from n value, you should not very confidently say this is the nucleation mode, this is the growth mode. To find out the temperature dependence of nucleation and growth for this overall transformation, and growth are thermally activated, so your n dot should be equal to n dot exponential. N dot is nothing but nucleation rate is there is an activation barrier of nucleation process, whatever the nucleation activation barrier, divided by RT or KT or mole of per atom, and there will be the growth rate also similarly. N subscript for nucleation, this G subscript for growth. Then your K is a function of temperature that I wrote. So this will be your because of growth cube, so 3j delta G of G over KT. So you can take so how can you determine experimentally the activation energy? Say for example you take Fv equal to say Fv equal to 0.5, say 50% after 50% transformation, your Fv equal to 0.5 meaning that is equal to 1 minus exponential minus KT to the power n. So your say n is 4, say n is 4 for the case n equal to 4. Say you assume certain nucleation process, assume certain growth process, and you came to this equation KT to the power 4. Now you want to find out the activation energy. What you will do? So now it will be ln2 equal to, it will be KT to the power 4 equal to ln2 from this. Your K is this one. So this T to the power 4 equal to constant. That means exponential this is constant. So this exponential part, whatever is this, multiplied by T to the power 4 is constant. Multiplied by T to the power 4 equal to constant. So you take ln of both the side, you take ln, then this divided by this plus 4 ln t will be constant. So if you plot ln t versus this, ln t versus 1 over temperature will give you the activation energy for the process. Now if you, so ln t versus 1 over temperature should be straight line. Now after doing that ln t versus 1 over temperature, if you find that it is not coming to be a straight line, then what to do? You understood? According to this it should be a straight line. If you keep on doing this, so ln time versus 1 over temperature should be a straight line, whose slope will be the activation barrier, which contains both nucleation activation barrier and growth activation barrier for the whole process. Now if you somehow ultimately doing all those things, repeating these Fv equal to 0.5 at different temperature, and then plotting ln time versus 1 over temperature, you find it is not a straight line. If you somehow find it is not a straight line, what will you do? You play with n. So n must be different. So whatever you assume, n must be different. You try with something else, 3 by 2, 5 by 2, whichever will give you straight line. Okay? How to measure Fv? How will you measure Fv? Will you guys give me for 15 minutes? No? 15 minutes. How many? Yes. Yes. vectors.